The purpose of Lab 1 was to go out into the real world and observe the motion of an object with a constant velocity. I observed the constant velocity motion of a soccer ball, rolling on a carpeted floor. I decided to roll the soccer ball on a thinly carpeted floor because I felt the soccer ball would roll easily on the surface and still give an accurate depiction of constant velocity. After I recorded the video of rolling the soccer ball, I put it into Tracker, which is this right here, where I then specified the video frames, the video time scale, and the video length scale for the analysis, calibrated the ball to a diameter of 0.22 meters, and then proceeded to use the coordinate system to describe the motion. I then identified the object's position in the video frames by continually plotting the middle of the ball in every single time frame. You can see that by all the continuous little dots in the center here. Doing this allowed the observed position versus time graph you see to appear right here, with the data collected shown below. The ball is moving along the x-axis in a negative direction. If, by chance, I had changed the orientation of the axis by flipping them or something like that, the data still would have been linear and the soccer ball would have still moved in the exact same way, still showing a constant velocity. As you can see from the table, the ball's initial position was at 0, 0, 0 meters. The calculations were done right here. As you can see, the ball's initial velocity was found by doing the change in position divided by the change in time. The initial velocity, which is also the average velocity because the time frame is so small, of the soccer ball was found to be negative 1.24 meters per second. The answer is negative because the ball was rolled from right to left, meaning it was going into the negative direction. I used all the information found in Tracker to create a model to predict the motion of the soccer ball using Newton's second law. But before I could create this computer model, changes needed to be made to the code in VPython. As you can see here, the mass of the ball was changed to 0.45. Also, the ball.bell and ball.pause were changed in order to go with our specific data. Ball.pause was 0, 0, 0, since our initial position was 0, 0, 0, while ball.bell was the same as the velocity we calculated earlier, negative 1.24. The time in the while loop, shown below, right here, was also changed to the final observation time from our video analysis, which was 1.167 seconds. This makes the lines in the while statement execute repeatedly until the condition is no longer satisfied. The pieces of code inside the while loop specify the net interactions for the predictions where the assumption is that they are at 0. Starting at initial position and velocity, there is an assumption of no net interactions from the surroundings with F net equals 0. Then we apply Newton's second law to predict the new velocity. Now, the change in velocity is always 0 because F net is 0. It is possible to say how the net interactions are equal to 0, however we would need a lot more information on the surroundings and the resulting pushes and pulls that we don't have, information about air resistance, friction, and drag force. The soccer ball's mass plays no role in the position because it leads to a constant velocity, so the position predictions would still have been good regardless of how large delta t was. This assumption is actually called Newton's first law, and basically Newton's first law says that when the system has no net interactions with the surroundings, the system moves at constant velocity. Now we see why it makes sense the velocity is constant and how that relates to the F net being 0. I used the new velocity to predict the new position, and then at the new time, I started over, and then the computer did the whole thing again and again and again until the time reached 1.167 seconds. This is also how the position of the soccer ball in the model is updated. After making all the corrections in VPython, I ran the code to get the model of my data, and as you can see, it looks similar to the motion of the soccer ball in Tracker. However, the graph will not be exact. This will be explained in just a moment. Now, I was ready to plot the model versus experiment graph, which is this right here. The graph shows the positions of the soccer ball at different times. The observed positions are shown with the dotted blue line, while the predicted positions are showed by the red line. As you can see from the graph, at early times, the observed positions lie exactly on the predicted positions line. This is because they aren't really predictions due to using my observations to set the initial conditions for my model. I did this when I used ball.bell and ball.pause. I used the first observed position and the time it was observed at to set ball.pause, which is the initial position of the ball, and t equals 0, the time we decided to start our clock. And we used the first and second observed positions and their times to estimate the initial velocity of the ball for our model. The rest of the predicted motion is really a prediction. As you can see from the graph, after the first couple points, the experiment data seems to veer off a little from the model prediction data. However, this is expected. This may be because there are other forces that are in play that aren't being taken into account by the model, forces such as friction, or air resistance, or maybe even gravity. It may also be because only the first two data points were used to predict the motion, and therefore other changes that happened after were not taken into account. If these other forces did not exist, then the data would emulate the model data more similarly. So, the computational model did predict the motion of the object quite well. However, with the forces that exist in our universe that are out of our control, there will always be even a slight difference between the experimental model and the actual model data.